So, since this is a bit lengthy code, let me start with an outline. At first, I'd like to discuss briefly very generic problems to deal with in the asteroid family business. Then we devote some time to methods we're using to simulate the orbital and spin evolution of asteroid families. And the most important part is part 3, devoted to uncertainties and systematic errors you can expect when you simulate asteroid families. And finally, I'd like to discuss applications, a few of them in the past few years, and of course, also the future applications of this calculation of future work. So regarding the problem, we take the families from the very origin of the planet, its orbital evolution, current observations. You have to deal with turbulence. And then inevitable thing, it's the very beginning. Then what we discussed yesterday, like many of the deterministic chaos, avoid it, especially in some places of the solar system. Then collisions are typical reversible process. You start with a highly ordered system, and during the collision you fragment everything which is completely unordered. So it's irreversible. And finally, sometimes you have to deal with a few number of bodies. So there is a stochastics, like Alessandro mentioned yesterday in terms of sample lines. And because of these 4 problems, force us to solve an inverse problem. If you just start with a synthetic family and proceed forward, you have to start with the task, and then you encounter the problem number 5, which are initial conditions. You cannot measure these conditions. You have to start t equals 0, which is not today, and usually you measure today. It's 4.6 billion years. And you have to use your model to compare with the observations at 4.5 billion years. We usually try to measure the orbital distribution. This is a sketch of the solar system. We have some major axis versus eccentricity and all bodies which you can find in catalogs. We mostly deal with asteroid families in the main belt. The structure is not visible clearly later on. And you can expect also families, observed families, also on the Hildas in the 3 resonance, and the Trojans. We have one family in the TNO region, the regular moons, and I expect the families will be observed elsewhere. So that's what we usually use as an observational constraint for our models. Now, regarding the methods, I can imagine we can divide numerical methods to 3 classes. One is hydrodynamic methods. We usually prefer the Lagrangian methods, which track the particles, simply because that during the collision you have trajectories which spread all over the solar system, so it would be difficult to have a regular grid. You have to use a method like SPH, smooth path vector hydrodynamics, which is indeed quite regular. I'm going to briefly discuss embodiment methods and one integrator which is of a Monte Carlo nature, which is used to describe collisions. Of course, any model, any type of model, requires initial conditions. Some of the models are also controlled by boundary conditions. And we have to think of parameters, mostly related to material parameters like density. And what is even worse, sometimes we have to plug in a parametric relations into the models, which is an input from a more complicated models, or more complicated physics, which we have to either believe, and we have to take into account also uncertainties which are very hidden in the parametric relations, describing, for example, fragmentation of objects. So that's what I'm going to discuss, either uncertainties, usually the uncertainties reported in papers, or quite often, are rather poor, because some of the uncertainties in initial conditions or parametric relations are not accounted for, and we have to be aware of systematics of this kind. features. It's a symplected scheme which uses a pick. It's a change of velocity of this kind. We get an acceleration, I'm going to use that later. Then it has a drift path, which is essentially a solution of the two-way problem in order to exploit the feature of the solar system that the mass is concentrated in the sun, so we can use it as the first approximation of the two-way problem. And then we have to account, most importantly, for perturbations caused by planets, which are expressed by the usual sum in the heliocentric frame. And then we are forced to add the following additional expressions. Sometimes you have to deal with the migration of planets. And one of the simplest models you can use for the migration of planets is the model similar to that of model of 1995, which is an analytical restriction of migration. It's an acceleration in the direction of velocity, and this would force planets to migrate elsewhere. Then you have to account for the thermal acceleration, the Yarkovsky effect, which is briefly speaking described by the relations above. These are expressions in the body-centric frame, then you could transform it to the heliocentric frame to apply the acceleration. You know, the MJ in the denominator of the thermal parameter, you see, that's something which enters the computation. It's a surface force, and any kind of surface force is driven by the surface area, of course, and the mass of the object. Major uncertainty, we shall see. Because it's related to the spin orientation, we have to account for the spin evolution. We are now using a very simple Euler integrator of this kind. We have a pre-computed set of torques denoted Fk and Gk. These are the torques due to the thermal emission. And we compute the evolution of this kind. Of course, we have to scale them appropriately to a given size, given some matrices, and given density using the formula below. And finally, we try to account for two additional effects of a collision of either of collision of origin or the effect of mass shape, which is occurring when you rotate too fast with shed mass. So you change the shape. This would change the York effect, etc. There are interactions between individual parts of this integrator. And the final expression, which is down there, is a parametric relation originating in collisional models, which describes three orientations. So that's the orbital evolution model. And then let me spend one slide discussing the Boulder code by Begrade et al. 2009, which is a code we use to describe the frequency of collisions and the evolution of the size frequency distribution. It's a on-the-cover model, so you have an estimate for the number of collisions, Nij, between targets and projectiles of a given size. It's controlled by the intrinsic collision probability, Pi, which might be in general dependent on time. It's not a fixed quality in the solar system. And there is delta T dispensation. Then you need to plug in calculation describing most importantly fragmentation of objects. The size frequency distribution of fragments. And this is described most importantly by the mass of the largest remnant. That's the next Q formulae. The mass of the largest fragment, where the size frequency distribution starts to rise quickly, and the slope of the size frequency distribution Q. So these were taken from Benz and Oswald SPH experiments, and we now take them as granted at this time. Okay. So that's the number of animals. When I showed this slide to my wife, she commented like this: I going to show the whole alphabet. Her jokes are sometimes annoying. So, how can we compute anything with this number of unknowns? So let me discuss, not all of them, but a few of these. What are the uncertainties? What are more or less constrained and what is not constrained? And you have to take it as a free parameter. So, first, it's not related to the objects. It's the family membership. Sometimes the uncertainty is dominated by the observations, not by the model itself, by the parameter, by the observations. Every model has to be compared to the observations. So that's the famous case, same major axis versus eccentricity, showing the region of Nissa-Ohana, where you can find clearly you can see two overlapping families, and if you look at the paper of Melissa Equis and Greenberg, you can find 5. It's completely hidden. And what is even worse, most of the objects are gray. It means they have no physical data on them, other than orbital data. So it's in principle impossible to distinguish interlopers. You have to treat them in a statistical way. And what is even worse than worse, the plot right here, even with physical data available, you can plot the geometric albedo versus histogram versus the number of objects that's for the EOS family. This world distribution is still consistent with an assumption of a fixed albedo. Okay? These uncertainties are simply photon shock noise present in infrared data. So even for a fixed albedo, you would end up with a very broad histogram, which is overlapping all between all different families. Let's go to number 2, which is the parameter size. It's an important thing to determine if you would like to compare your model to the observed families, the collision model to observed families. We usually use a simplified scaling as devised by Jorda et al. 2007. The problem, the uncertainty of the parabolic size is dominated in this case by the fact that multiple bits have the same chi-square. We have a huge set of 150 SPH simulations, and we try to match the observed chi-square distribution to the synthetic model. It's a very simple procedure, and the shape leftwards or rightwards is the scaling. It's a simple procedure. For the EOS family, we will end up with this parabolic size versus table chi-square. You see that 350 plus or minus 25 is the result of the EOS family. And you can estimate this way also other parameters of the impact. Here, impact velocity versus the parabolic size versus projectile versus angle. Of course, you can guess the systematics. You believe the SPH models, which is not always reasonable, okay? Especially one warning is important, that the SPH models do not always show a convergence when you increase the number of SPH particles. Okay, it's a great warning. So we use them, okay, we believe them, but only for a short period of time. And then we need to discuss the possibility that the SPH models are wrong and consider that the parabolic size are wrong too. It's got to admit it. Number 4, initial velocity field. Something which we again try to avoid by a very simple assumption, and that's complete isotropy and a Maxwellian distribution of the velocities, which is a peak at about escape velocity from the parent body. I think it's a simplest assumption. We can use those fragments to escape the parent body. So most of the fragments will have the escape velocity. It's okay. But it's not always the case for all the families. One of the famous cases, which is definitely not isotropic, is the very standard, for example, in use. And we have 2 problems. The uncertainty is related to the impact geometry, to the true anomaly of the impact, and to the longitude of Sometimes these two omega can be constrained, as we shall see later on. And the systematics are, of course, that the initial velocity field was indeed anisotropic. This is a result of a SPH model, SPH plus cavitation or accumulation model. That's the histogram, which is roughly Maxwellian, as I told you, that's okay. But if you look at the distribution of velocities at late phases, that's after the accumulation is gone, you see that there's a structure which is definitely not isotropic. So we should understand this difference. That some of the techniques appear to be isotropic, but the SPH model shows us the contrary. They show us a sort of race in the distribution of fragments. Number 5, density. Something which was discussed by Paolo this morning, so let's not spend time. I just want to emphasize that the distribution of densities, if you focus on the high precision measurements, these are from Carey et al. If you focus on the dark gray dots, for example, these are better than 20% certain measurements. The distribution of densities for these C-type asteroids is definitely not Gaussian. And because this dominates, usually dominates the uncertainties of a model, the distribution of your results is not Gaussian. You simply can be wrong, your density could be different, and if you report the results as the mean value plus or minus something, you would create a false impression that your distribution is normal, which is not true. Porosity is even worse case. There is a low number of asteroids which have measured value of porosity, and regarding the calibration, one of the most precise measurements is for venue asteroid, which was studied in great amount of detail. But not all quantities for venue are measured sufficiently precise. If you use it as a calibration point, then all of your results might be shifted in a systematic way, in a non-random way. So, for example, the shape of venue and the shape of your asteroids might be systematically different. So this would create a difference in your model and in your result, which is not random, which is systematic. Number 7, I'd like to show distribution of thermal inertia or thermal conductivities versus sizes from Marcos paper 37. You see that there is a trend, but it might be the case that it's around a step-like function. You can measure it by a step-like function. So this is one of the things you can play with to assume a different distribution of thermal conductivities for large and small objects in the simulation. Regarding the systematics, all of these data were computed using a NIE thermal model, which is suitable for spheres, not for real shapes. If there are any problems in this, then we have a problem with our computation. Regarding the state, we usually assume, again, an isotropic spin just after the disruption and a Maxwellian distribution of spin rates. Okay, a very simple assumption, but it's only an assumption. If you look at the observed spin states, that's the plot below, rainbow, and the color correspond to prograde or retrograde objects, which were inferred by Lanchet out 2013, which are included in the database. The uncertainties of these points are about 10 degrees in polar latitude. The longitude is, of course, less constrained. There are often multiple solutions which are mirror solutions in longitude. So I would recommend to use mostly the latitudes of the work. It's impossible not to speak about shape. And the question is, major question is, what is the correspondence between the models of shape and real shapes? One of the pronounced examples is Hector 664 Trojan, which shape model, complex core shape model looks like this, and actually it's a very example. You can imagine that properties of this asteroid is completely different from the properties of this model. So that's the reason why we do not use these shapes for the computation of your torus. We simply use a large set of shapes which are somehow compatible with the observed shapes, but we assign them randomly on a random basis. I mean, the torus to particular objects, which is, I think, which is reasonable because even the small scale topography, which cannot be captured in this model, shape model, affects the resulting York field. So I think the best solution is to assign it randomly and play with the C York value, the scaling of the York value. And finally, let me warn you that even individual boulders can affect the York torque, consequently your historic family model. We try to address this together with Sherecek et al. We computed heat diffusion in 3 dimensions, realistic boulders sitting on the surface of Itokawa. We extracted the size frequency distribution of boulders, and that's the one. And we sum up all of the surface and come up with this rate of change of angular velocity. But you know what a realistic shape means. You cannot tell what are the real shapes of boulders. It's impossible. Know that there is a hidden assumption right here. You have small snapshots of Itokawa's surface, and if we assume something about the surface which was not seen at this resolution. Okay, so 2 major assumptions which would entirely change the spin evolution of Itokawa.
There's also the work of bench here that shows that if you displace the
center of mass.
Center of mass.
Exactly. That's the work, the paper by Lowry. I agree. That's
another
sort of alternative explanation that the center of mass is not fixed. Exactly. Thank you for this point. I'm not going to go into this finite element which is used to compute the heat diffusion. But let me discuss the internal structure. Another important point. There is an ongoing discussion whether the asteroids are mostly monolithic, or they have a macroscopic porosity, or a sort of internal microporous material. The 3 papers are related to these 3 possible structures. We tried to address this in our paper, I thought 2014. We constructed a model of the main belt, divided them into 6 parts as this one. And we were able to fit both the size frequency distributions and the numbers of families in each of 6 parts, even though the fits are not perfect. Okay? Especially at small sizes, we have a systematics which cannot be easily avoided. We started with 200,000 collision models, and this is the best fit. It's extremely difficult to fit the small size in. But what is important? The fit for rubber tiles is even worse than that. And this surprised us when we saw this for the first time, because it might indicate that the macroporous rubber tiles are not present in the solar system. The porosity is rather of microscopic nature. Number 12, the scaling law, the usual relation between strength and size. Uncertainties are mostly related to material parameters, of course. And what about the systematics? I want to emphasize 2. There might be a velocity dependence, which is not included in the formula above describing the or there might be important impact angle scale, as suggested by the adapters. Moreover, let me warn you that often the models indicate the total damage of target. It may mean that we actually produce a lot of dust, and dust behaves differently than individual particles. These are clouds of dust. We do not account for bouncing and friction. So if there is a reaccumulation event, then you can bounce all over the surface, resulting seismic distribution might be very different, as suggested by Richardson et al. And finally, if the collision is energetic enough and you create a vapor, then everything is wrong. Everything. Because you create a hot gas which can exhibit a chemical relation. So you definitely cannot use a single equational state like Watson 1960. And finally, we have to move on quickly. So regarding the more evolved models, we have to plug in sometimes a prescribed scenario for planetary migration. That's the scenario in this day to describe the evolution of the planetary system during the LHB period. You see the evolution of 5 planets with one ice giant being ejected from the solar system. The uncertainty here is the mass of the disk. And systematics, of course, the scenario in future may come with a different scenario which is even better describing the evolution of planets. And what is even worse, there might be present additional populations in the solar system which would cause additional bombardment to what is seen today, like the evil suggested by Hawking. And when you play with planets, of course, you disturb your population. For example, the main belt is depleted usually by a factor of 3, suggested by Newton and Malhotra. This is the depletion versus time. And collision probabilities versus time are again not fixed. And I think this is the final one regarding the uncertainty of systematics. This is the size distribution of comets. When we studied nuclear families during the LHB, the electric compartment, the major uncertainty was related to the size frequency distribution of comets, I mean trans-Neptunian objects, which were providing the inner solar system. Actually, the only way how to constrain the slope of this size frequency distribution is, for example, the observation of Neptune trojans, which were captured during the evolution of the solar system. And this is probably the most pristine population in the solar system. So we shall rely on these measurements, but let's have a look at the error bars. Okay, so we move on to applications. First, we of course try to apply these models to individual families. I'm going to show you a EOS family down there, always the major axis versus eccentricity. These are observations, but not all of them. We selected the observations of K-type asteroids, which have a distinct taxonomical class. You see that they are really spread all across the region. And then we constructed a model which starts in a simple way with an isotropic disruption, and we proceeded end up with this complicated structure. You see, it's almost unbelievable that from this very simple ellipse, you would end up with this very complicated shape with different number densities of objects. But the reason is that there are a number of resonances, resonances present, and moreover there is a secular resonance cutting the family just in the middle, so we can create a very complicated shape in the course of time. And I think that extracting this complicated shape from even a uniform background would be a difficult task using the hierarchical clustering method. We shall maybe rely on n-body models to extract these complicated shapes. Now let's discuss families as a whole, statistical sample. We tried to construct a so-called production function, which is bit misleading because it looks like a size frequency distribution, but now this is the distribution of parameter sizes of families with respect to the size. So you can see that we have about 20 families with a parameter size larger than 100 kilometers, and moreover we have a number of craterings. That's the black curve. And these two curves seem to converge in the sense that if you identify the families again and again, at least the red curve does not change substantially. So we think that the sample families larger than 100 kilometers in which are catastrophic disruptions are complete. We are not missing families of this size. Let us see the ages. Of course, if you can try to plot ages versus parameter sizes. Well, what is the age? Actually, this is the upper limit of the age using the so-called V-shaped envelope. In most cases. Some cases are modeled more properly, but something like this. I think there are two features worth to mention. First, the ages of the large families span the whole interval from 0 to 4 billion years. We have no families which are, say, 5 or 6 billion years old, and we have at least a few cases which are approaching 4. I think this is a lucky observation because it may indicate that the parameters, the nominal parameters we use, are not systematically offset by a factor of 1.5 or 2 with respect to the solar system. And there's a motivation down there. The region is completely empty. We have not found any family which is smaller than 100 kilometers size, and it is old. It's worth to look for these, or remnants of these families in the solar system.
Also in the middle we see that
Yeah, right. They might be sort of right. Maybe something is wrong with our determination. Maybe these ages are somewhat underestimated. I don't know. Of course, there might be systematics all over this figure. So, letter D. We were interested also in the role of the lazy bombardment on the main belt. That's again a production function, but now for a synthetic population, for a synthetic main belt. And we tried to bombard it with comets, and we end up with the blue and black curves. You see the curves are very diverse because the model is stochastic. It's useless to compute one simulation. You have to compute at least 100. And then there is a huge mismatch at 100 kilometers. The mismatch is a factor of 5. So even though we have no problems producing families 200 kilometers in size and larger, we have problems producing too many families of 100 kilometers size. We think we can get rid of them by invoking two effects. The first one is a secondary bombardment. We should account for it. The family is not present and fixed in the solar system. And we need also the help of breakups of comets at low planetary distances to somewhat decrease the flux of comets from the P&L region. Letter E, I think this is almost the last one. Both slides, the last slides, are motivation for looking for all families. And we think that the best zone, the best part of the main belt, is the zone so-called pristine between 2.85 and 2.955, where we have a very low background density and contamination by background objects. We think that some of the families, for example this one, are actually a remnant of a very old family. I like this. also the distribution of spin states. I think that we were at least partly successful in terms of the whole main belt. This is the distribution of betas, of latitudes, of psion latitudes. The black is the observed distribution, and the gray lines are again 100 models. So you see that at least for small ones, we were able to roughly explain the depletion of the observed population at the very center. And we actually use the result of this model to constrain the CDOR parameter. We need to explain the observed population of the model. And then we tried later on to match even the individual families. There are 3 which have enough observations, but unfortunately this number is not enough to have an uncertainty which is dominated by the model. We have an uncertainty which is dominated by the low number of observed objects, which is big. So the flora family seems to be great. You need a quite a complicated model to fit it, but we need to wait until a larger number of objects will be available. So that's a sort of intermediate summary what I have told, but I think we shall move on to future applications. So I think the way to go with the asteroid family business is the following. Either use a brute force. To observe what is not observed. We try to take a part in this using a robotic observatory, which is supposed to be working this year, and in the course of the next few years we are going to observe so-called targeted photometry to get measurements of asteroids which are suitable for the derivation of shapes and modes. I'm also awaiting new observations of surveys which should cover sub-kilometer asteroids, because this would constrain mostly the York evolution models. These are very suitable. Then I think it's worth to use the new NEO model, which is completed by Mikhail, because the resulting size frequency distribution might be a very strong constraint for any collisional models of the main belt and consequently families. I already mentioned the Neptune Trojans, and I have to emphasize that only a limited number of families were studied by n-body models. I think we shall proceed with this to understand families on a one-on-one basis. And finally, we think that the Trojan families might be quite suitable to study, for example, the original velocity field, because in the zero order resonance, we have no substantial Yarkovsky drift, so the orbits are more or less preserved in the Trojan region. Regarding the collisional models, I think it's worth to calibrate the models using the observations of young families. Of course, you have to determine the completeness, and the sample will be complete only for a limited period of time. So new families should be searched for and should be dated in order to include it in this business. Then it would be worth to have a model, collisional model, which accounts for both monoliths and rubber piles and accounts for their interactions, because fragments of both may serve as projectiles for the whole population. We shall include the York spin-up disruptions suggested by Epopson, 2014, and decide what's more important, in fact, collisional disruptions or Yarkovsky removal or the York spin-up. And finally, I think it's time to proceed with a new kind of models which do not compute orbital and collisional evolution separately, but take them together. One should probably use an approach like Levison et al. 2012 in their LightLab integrator and trace particles in order to cover the whole size frequency distribution. finally, there is a note on three-dimensional heat diffusion and more boulders, more shapes, in order to have statistics on possible your torques, which are created by boulders. That's the very end. Regarding the SPH simulations, I think it's worth to analyze the velocity fields, but with the warnings you mentioned a lot before. We should definitely improve the scaling, which is the simplest scaling you can use today, scaling 100 kilometer targets down or up. We should perform the SPH simulations actually. And maybe regarding the LHB period, it's worth to simulate even high-speed collisions with very deep projectiles, which correspond to comets. Thank you for
the time. We'll start with Marco.
Thank you for the talk. So I'm kind of on your 3D or D2D heat diffusion model. For example, do you assume that the boulders have homogeneous composition, or they can have voids? If you have voids, the heat transfer is by photons, by photons.
Sure. At this point, we completed a single boulder in a single shape, which seems realistic, and which is homogeneous. So we prescribe its conductivity, which is corresponding, I think, to 1,000 watt. Yeah. So you're right. It's worth to account for a more complicated structure. In principle, the model allows it because it's a finite element method, so you are not constrained by geometry. And maybe it might be a problem with voids, internal voids. I'm not sure if we can account for that.
I'm interested in that you can help for the thermal tracking too, because you can have better feel.
Sure. And the cracks, actually the cracks itself, if you not speak about the heat diffusion, are easy to implement. So you drop the triangles and the tetrahedra and the interior into the vacuum.
I'm interested on the first point that you have here in your last slide, the analysis of velocity fields resulting from SPH. The reason is that we have just submitted a paper with under the Loro Paolo or Paolo Posticci. The problem that we have is that we want to understand how there is a reaccumulation of this on the fragments produced predicted by these models. Because in the past we were using a semi-empirical model of ejection velocity fields in this kind of events, and we did not find any possible accumulation. So we are trying to understand what are the properties of velocity fields that allow for the accumulation. And some preliminary results suggest that this is due to the fact that just from the beginning, some of the trajectories are already intersecting, and there is also some kind of wavy dependence of the velocity on the position, and this makes it possible that some objects collide with some.
You simply catch up
something like that.
And
so this is, I think, this is very interesting and complicated problem that we should try.
With a number of effects, we could affect reaccumulation. It's worth to try.
Yeah, because then this drives the size distribution that will be at T equals 0. Okay,
So you mentioned that the depth of a void in the plot of all of them is below 100 kilometers. But you also mentioned that this limit is about the limit of completeness of the current sense of families. So there will be smaller objects for which the number of families is not.
I think that we have an indication that the sample is large enough that we should see something. Okay? If you look at the production curve,
Even taking into account observational
I think so, because if you look at this point,
yes,
in the middle, it's still increasing.
yeah.
Okay? So we think that the completeness is, of course, not 100% below 100 kilometers, but we should see something. long-term revolution which is efficient enough to destroy everything, and you have only a few objects remaining, and then you need to be courageous enough to interpret it as a remnant of an old family. It's a bit speculative or paper, but we shall be aware it's indeed a possibility that few large objects remaining are actually remnants of a big family.
I will make one last comment about what you said about the fragmentation of the modeling of collisions, large velocity between comets and asteroids, which is also a puzzling thing because in one of the versions of the model, for example, we were capturing too many comets, and the only way to explain what you see essentially is to assume that they are, because they are much more trivial and probably they have a different aspect of distribution, they are not as effective in breaking up and creating families. Essentially, they destroy themselves in the collisions instead of destroying the family.
You mean the paper by Lewis?
Yes. Because this is also consistent with a lot of micrometeorites that are similar to the comets. Anyway, so if there is no other question, thank you very much.